25-minute mark. I might end a little bit early, but I don't know. Sometimes you say that and that doesn't happen. So we'll see. But yeah, so I'm going to be talking about an out of equilibrium search for the QCD critical point. I'm going to try and make this a little bit of a pedagogical talk. I haven't seen that there has been too much discussion on hydrodynamics so far yet in the meeting. And I think that there's an email that said that there'd be an appreciation if there was kind of like a focus on concepts. So I'm going to try and make this a little bit more pedagogical talk, but also at the same time introduce some kind of more results, some newer results that have just kind of recently come out. So go ahead and get started. First slide here. So we're talking about this. We want to kind of model, we want to do our best to model heavy ion collisions, right? And so if I'm going to start it pedagogically, I can kind of start out by talking about the different stages of a heavy ion collision, right? So you have your initial stages here, circled in blue, your kind of aftermath of your initial stages going into your hydrodynamic evolution here, circled in green, and a hadronization and some phase transition, freeze out, maybe some rescattering here, circled in orange. And these things are kind of all connected here, kind of Venn diagram-ish. And that's done on purpose, actually, because there is some uncertainty kind of like where, you stop using one model and start using another one. And like, do I do, hadron rescattering and all these kinds of questions, right? And they're disconnected fundamentally from this red circle here, which is what you kind of trying to show that what we measure in charge space at the end of the day, or measure experimentally, is fundamentally disconnected from our theoretical modeling, right? So the real challenge of heavy ion collisions is trying to relate this complicated theoretical hybrid models and relating that to the experimental measurements that are somehow fundamentally disconnected from all this here, because one can never measure any of this stuff that's going on there, right? So we're heavily reliant on our theories and our model building in order to tell us what's going on there, right? So in that sense, it's really important to get your theory right. You have to really trust and believe your theory. So that's going to be a kind of the main focus towards the second half of this talk, just to kind of get us started. But if I want to start talking about far from equilibrium hydrodynamics, I want to talk about far from equilibrium search for the QCD critical point. I need to start talking about far from equilibrium hydrodynamics. And I think the best way to do that is start talking about where we know it best, which is at LHC and vanishing baryon chemical potential. At those really high energies, TeV scale, you have nuclei that punch completely through each other and leave a deposition in their wake. And that deposition is just some deposition of energy and evolves hydrodynamically. And it actually has, on average, a net zero baryon density, so zero baryon chemical potential, which means that we can calculate it on the lattice, right? So the nice thing about LHC is that we know the equation of state. Like from first principles, we can go to the lattice and calculate it because there's no Fermi sign problem. And the QCD equation of state there is only a function of temperature. So we can use that and plug it into our hydrodynamics and plug it into viscous hydro with no conserved charges and do very well to describe low PT particles for a broad range of collision energies. There's many models on the market that people know about. There's VHP Hydro, Music, Vishnu, and there's current efforts going on to constrain exactly what the initial conditions are. But historically, this is done really well to explain or to reproduce data at a broad range of energy collisions from TeV scale to GeV scale and around a broad range of different kind of systems, from lead, large systems, to P-lead, what we would consider small systems, where we wouldn't necessarily expect hydrodynamics to work. So what is the deal with all of that and far from equilibrium hydro? You can't really talk about far from equilibrium hydrodynamics without talking about the concept of attractors, which seems to be a robust feature of kinetic theory and different hydrodynamic formulation. When I say attractor, I mean something along the lines of I have some broad range of initial conditions, and everything on some short time scale collapses onto some universal non-trivial curve, right? So my hydrodynamics, my relativistic hydrodynamics, exhibit some sort of universal behavior before the system reaches equilibrium, for instance, right? And it's the existence of these attractors that makes us think that far from equilibrium hydrodynamics is plausible and even likely in small systems, where I might have a system that looks like this bumpy system over here in the bottom left corner with tons of large gradients and spikes everywhere, just because I don't have a large system that smooths out all of these gradients. So this is how we kind of make sense of it. But unfortunately, it's sort of a blessing and a curse, right? Because while it does offer a means to explain the robustness of hydrodynamic predictions, for a broad range of collision systems, given the far from equilibrium initial state. By their very nature, they imply a memory loss of the system's initial condition. So it's very hard to make it's very hard to make theoretical constraints and detect those what's implied by those constraints because of that. So basically, this means that I can put in any model and kind of like finagle it around and get something out at the end that makes sense, right? So there's two sides of this coin there. So how does this look for, but how does this all look for a toy model hydro with some realistic equations in state? Do we still get attractors, right? So now we want to explore the concept of attractor a little bit more. In order to do this, we're going to use a highly symmetric version of hydrodynamics called Bjorken flow, where the relaxation equations have boost invariance and polar symmetry. The main thing that I want you to take away from this slide here is that for DNMR hydrodynamics, unlike something like Navier-Stokes, the viscous currents relax to their Navier-Stokes values, but are actually independent dynamic variables. So these are the equations that govern how they evolve hydrodynamically, and they're initialized independently of your initial energy distribution and independently of your initial flow. So these guys here, these two pi's, are really their own independent dynamical variables that you have to initialize on top of everything else when you do your hydrodynamics, which is really solving this energy conservation equation here in this highly symmetric case for Bjorken flow. Okay, so, and these you saw the sneak peek at these on the previous slide, but if you take this case, a simple case with a constant relaxation time at 0 chemical potential, you do see that you clearly get attracting behavior. So this is kind of not really a surprise. All we did here was turn on a bulk, right? Turn on a bulk and also turn on finite chemical potential. But one might ask whether or not all these evolutions are physical. Does it make sense to run all of these different initial conditions? Like, yes, I have an attractor and I have, a sense in which all of these initial conditions will collapse into a universal curve and eventually look like something in equilibrium. But did it make sense to run all of these evolutions in hydrodynamics? So that's something that I should have done in the first place. So in order to answer that question, you need a fundamental constraint from theory. And one way to do that, one way to go about doing that, since Knudsen number and Reynolds number aren't necessarily doing that for us anymore, is to talk about causality. And the fact is that the existence of an attractor is not enough to guarantee that it makes physical sense to use hydrodynamics. And once we start wondering about this unreasonable effectiveness of hydrodynamics in small systems, for instance, but also for any heavy ion collision that's initialized far from equilibrium, these issues become evident and we have to face them. So in this paper here, Benfica et al., they derive constraints for guaranteed subluminal signal propagation in deterministic relativistic hydrodynamics. So for DNMR equations of state for the people, or DNMR equations of motion for the people who are familiar with that. Basically, because the ones I showed earlier, except not as symmetric. Some of these studies have already been done at mu b is equal to 0. So you see that there's been, on the left here, we have some IP Glasma and mu. So IP Glasma is an initial condition, is used in heavy ion collisions as an initial condition that's based on the CGC formulation that we heard a little bit about earlier. And music is a state-of-the-art hydrodynamic code that is available publicly as well. So you see here that the red is all a bunch of causality violating hydrodynamic cells. Over here on the right, you have kind of a scan and phase space from this nice paper here, where they show scan and phase space given some transfer coefficients on what are the largest values for my viscous currents that I can have, and my system remains causal. I'm not going to say too much about these papers. I just wanted to kind of give like a little bit of a synopsis on those. But if you're interested in this, do look at both of these papers. They're really interesting, and I think they're very important for our field as a whole. So at the end of the day, I am giving a talk on looking for the critical point with an out of equilibrium scenario. So in order to talk about that, I want to start talking about the beam energy scan, because the beam energy scan is really, or the search for the critical point is really an experimentally motivated, experimentally driven question in our field, right? Because at the end of the day, all we have are theoretical models, and we can't measure anything except for the final state, right? So the main objective is to probe the behavior of the QCD, QCD in the baryon-rich regime, and look for possibly the onset of criticality or for a first order phase transition. But this will be complicated by lower energies, finite lifetime effects, out of equilibrium effects, which I focus on here. And we want to kind of start to wonder what are the effective causality constraints on our modeling for the beam energy scan. So on our modeling for what the data, what we should measure at the beam energy scan, what kind of constraints does this causality put on that for us? So if I have different initial conditions going through some freeze out point, right? How are my trajectories constrained given that I have these causality constraints? Given that now I know that I can't put whatever I want to put into my hydrodynamics and evolve it, what happens to these trajectories? You can see here, for instance, that for these trajectories over here, I have some final state degeneracy. That is that all these different trajectories that start at different chemical potentials, they all end up at this point in the phase diagram here. So if I freeze out and I measure that, okay, this is where I was in my phase diagram when the system froze out, I don't know exactly where I started, right? However, if I can use causality constraints, for instance, to remove some of these trajectories, and I know some of these trajectories will be unphysical, then perhaps I can make a better educated guess as to what my initial condition must have been, for instance, right? Now, strictly speaking, I really want to make this note clear. The causality analysis done in the paper that I showed was done for the case of no charge dynamics. But under Bjorken's symmetry, it's actually expected that the results will hold. And if you have more questions about that, we can please do ask about it later on. But I'm not going to say too much more about that in the rest of my talk. But it is a little bit of a leap, but they're expected to hold, and something about that could be out relatively soon, possibly. Also, in order to study criticality and hydrodynamics effect on it, you need some sort of phenological tool because we don't have the equation of state of QCD at finite chemical potential. So I have this equation of state here, this best collaboration equation of state, in which you put a critical point by hand into the QCD phase diagram, where you make sure that it matches lattice QCD at zero chemical potential, and close to the temperature axis, the system without the critical behavior is just taken from a Taylor expansion in mu b over t, and then you kind of paste on this 3D Ising model universality class critical point and do the matching and make sure it's all thermodynamically consistent. And this gives you an equation of state that has the physics of QCD at mu b equals 0, but then has critical Ising model universality class at higher chemical potentials. The point is that ideal hydrodynamics will evolve you from start to finish from along these isotropes of constant S over NB. But now that we're going to be talking about out of equilibrium effects, we want to see how these trajectories will be influenced and what the role of causality will play and what happens to the trajectories. So this is, again, just another slide kind of emphasizing the same point. Close to equilibrium, you have this black line here, right? Or in equilibrium, you have this black line here that's really an isotropic trajectory. Close to equilibrium, you might have something that's not too different, right? Kind of like this green line here. But far from equilibrium, you might have something that's extremely different, but you want to ask whether or not these trajectories are physical. So just to remind you what the model was, these are the DNMR equations of motion. Now, on top of that, we're just solving, we're just adding in this equation of motion here on the top right. That tells us how the baryon density evolves in time. And actually, the fact that that there's no charge diffusion in the Bjorken scenario is actually key for applying the causality analysis in this context. But you get these non-trivial paths in the phase diagram that are driven by this epsilon of t dependence, as well as this mapping from the equation state. So does far from equilibrium hydrodynamics still make sense once you include finite chemical potential? The answer is, I mean, pretty much yes, as you kind of would have expected. You can see these potential attractors that persist at finite chemical potential, so far from the critical point. Here you see these arrows that point in the direction of the last time derivative, right? So you see that while all the lines aren't kind of at the same point yet, you can see that they're kind of on a line here, and they're all kind of like going along here, and that's why we refer to it as a potential attractor, because they haven't really come to each other yet, but you can see that they're kind of getting there. And the same thing's true as here, close to the critical point. So this is for the pi, the shear channel. Close to the critical point, you also get kind of this potential attracting behavior there. In this so for these runs, the criticality was incorporated not only through the equation of state, as I already mentioned, but also as well as with scaling the bulk viscosity as well. And this is the same thing, but in the bulk channel, you have kind of these potential attractors. Well, actually, well, these they really look more like attractors than they do in the previous slide, which was actually surprising in the end, because the bulk the bulk viscosity has a scaling that goes with the correlation length in this equation of state. It goes like correlation length to the third. So we had expected that if this was going to break anywhere, it would have been in the bulk sector, but it turned out that this wasn't the case. The system still exhibits this attracting like behavior, even in the bulk sector, even when you go through the critical point, which was somewhat surprising in a sense. But okay, so what does this mean for actually exploring the phase diagram? Well, it means that out of equilibrium effects are important, right? So if what I have here is all trajectories initialized at the same energy density, 3 different baryon densities that you initialize at, and then a plethora of different shear and bulk, right? So this chi and omega are the same chi and omega from over here. It's just the unitless versions of your bulk pi, your bulk pressure, and your shear. But what happens now when you turn on the causality analysis and take away the trajectories that don't behave causally? Well, you get this, right? So it does actually cut down on your phase space by a good amount. So as dramatic as this plot is here, it's nice to know that once you implement kind of physical checks, you can kind of get rid of some of this uncertainty in your final state that we've been talking about here, right? So if I take, okay, so this is a nice little video that I have here where basically I take, shows the evolution of these trajectories here. You'll see the blue points are points that are behaving causally, the red points are points that are behaving acausally, and the purple points are points that are behaving kind of indeterminately. I just want to start it again just so I can make a point. So all of these points are done with the same initial energy density, and there's every point here has there's 3 points on top of each other here at every pi for 3 different baryon densities, initial baryon densities. These are the same runs from the previous slide. And you can already see that right at the beginning, you know, there's a large section of your phase space that is just off limits due to the causality violations. And so now you can kind of see evolve. And most of the points that started, or the points that start out causal all remain causal, but most of the points that started out acausal become either causal or indeterminate. And so what's happening here is as the system freezes out, they turn into X's and they stop evolving. So most of them are either freezing out as being causal or freezing out as being indeterminates, which is kind of expected in a sense, because as your system equilibrates, it looks better and better and better, but that doesn't mean that the system started out causal, or that you should have continued to run that hydrodynamic simulation, because at some point it became acausal. So at any point they become acausal, you really don't really want to trust what's going on. You really don't want to trust your formulation there, right? So, and so this will continue on and not much else really happens here, but I just think it's a nice little video, a nice little visualization of what's going on. I really like it in the beginning when they're kind of all swimming around. Right, so now if we look at the same plot from earlier, we have the unconstrained version on the left, where we have different baryon, where we do a scan in different baryon densities, a scan in different initial out of equilibrium conditions, all at the same energy density, coming to some final state here, where you have this degeneracy from your initial state compared to your final state, and you run the causality analysis and you get rid of a large chunk of that, which is very good in a sense, right? Because now I have an idea of how to start to limit the phase space available to me in my hydrodynamics, right? And the same thing's true here for the ones that go through the critical point, right? I get rid of a bunch of these trajectories. So it turns out that this ensuring causality is highly constraining, and especially as when applied to the previous analysis that was done here, right? So yeah, that's about all that I have. think that I'm probably a little bit early, but I don't know if anyone's going to complain about that. There's still much theoretical work to do. There's still much theoretical work to do in terms of modeling for the upcoming beam energy scan too, but these results showing that ensuring causality may offer a robust solution to constraining initial conditions in hydroevolution in the search for the critical point. Future work will be done in studying the interplay between attractors and causality, not only at μb equals 0, but also finite μb, because there can be an interesting interplay there as well going on. But yeah, so that's about all I have.
Okay, thanks for this nice talk. And we have almost 10 minutes for questions. So that means 10 questions that you have to answer in these 10 minutes. Okay, so I saw one which already raised his hand.
Yeah.
Can go ahead. Okay, yes, go ahead.
So hi, I have one question which is a bit on the tangent of what you are telling. So shock waves, shocks, they are typical phenomena if you have a first order phase transition. And they are discontinuous solutions of ideal hydrodynamics. Yet they are known to produce entropy, which is very peculiar for ideal hydrodynamics. And the reason is that essentially if you go to the shock itself, there is a region which is matched by hydrodynamics, but that lies outside the validity of hydrodynamics. The gradients at the shock are just infinite, mathematically speaking. So I wonder whether you have any thought about whether it has something to do with what you are talking about. Because in principle, you would expect that if you zoom into this region around the shock, that you identify behavior that has nothing to do with hydrodynamics. Mm-hmm. And yet ideal hydrodynamics is known to provide a good description of that. So you would flag possibly something with your mechanism here that would be a feature rather than an artifact.
Mm-hmm. So your question is, I guess, because if I were to run this kind of, well, okay, so one thing is ideal hydrodynamics is known to always be causal. So you couldn't run this kind of analysis if you're running ideal hydrodynamics, but maybe I'm misunderstanding exactly.
Well, okay. Let me turn it a completely different direction. If there are many works in the literature where you ask whether something is hydrodynamic by asking whether the elements of T mu nu that you analyze satisfy hydrodynamic consistency conditions to some order. So this is essentially the question to what extent T mu nu locally can be described in terms of a gradient expansion. Okay, and that is a test where the dynamics could still be causal, but where you would flag that something is inaccurate by stating the gradients are too large for a gradient expansion to be reliable. Mm-hmm. That would be a quantitative assessment.
Yeah.
Now, what you do, you don't do that. You limit your dynamics by a causality constraint instead. And of course, it could be, for instance, that you operate just in a system that has so large gradients that it cannot be described hydrodynamically.
Yeah.
And causality would be either a byproduct of the description not being applicable, or it would be, so it seems to me you elevate the notion of hydrodynamics to say that is always right, and I can use this description even to limit the dynamical evolution, while I would think shouldn't be the argument the opposite. I just wonder, and
I don't think that hydro is always right. And I hope it didn't come off like that, right? But part of the big reason why I spent so much time in the beginning kind of going through the historical aspect of it is because historically it has done really well when you in systems where you wouldn't expect it to do well. And actually, if you look at even so, if you look at either of these papers here, both of these papers analyze kind of state of the art, in some sense, models in our field, where you have models that are able to reproduce data, right? Able to reproduce the collective flow, for instance, that we see in data that is like interpreted as a fundamental hydrodynamic signal.
I have high regard for these models. I'm just curious about how you think that, how do you apply this logic? Because what you say, I have a dynamic description, DNMR, which is certainly a state of the art. And now I use an additional constraint in order to do what? In order to exclude some of the possible evolution histories. Is that true?
Yeah, well, because the main point is that because of this tracking-like behavior, you lose information.
And here I wonder, the trajectories that you exclude, couldn't it be that they are in principle valid trajectories, only that they are not well described within hydrodynamics? Well, I just wonder, because you turn it around, you say, since they are not described by hydrodynamics, they are not valid trajectories. I just wonder about the logic with which you, what is that the way I have to understand what you are doing? You show us a set of lines, and then you say, oh, these lines, they are accorsted, so I can forget them. While previously we have said, oh, these lines, they violate certain conditions on smallness of gradients, and hence I should follow these lines dynamically differently. I wouldn't exclude them. I would just require that I need another dynamics to follow them.
You can produce some dynamics that produces those lines, the same ones, then that's great.
Okay, so I think I have to stop the discussion here because we have 3 minutes, and we can talk about it later on because we have 30 minutes after the last session. So I have only 3 minutes. So if there are any other questions for other people to join, but this discussion is important. So I think we will postpone it to the question and answer sessions after the last talk.
If you allow me to say, it was a very nice talk.
Yes.
Stimulating. Okay.
So George, I think you have some, so if you want to talk.
No, I was just basically going back at Ur's comment. It's just that I think you're both trying to say the same thing. The point is that with this description for these equations of motion, you cannot trust those trajectories. But of course, if you change what your theory is, then those trajectories may become physical and relevant again. So this depends on the tool that you use. So the point is to say that the tool could not admit those solutions, but it doesn't mean that another tool will have the same result. It's just that's the point.
Okay, so I may. Okay, so I may ask, what will change if one use, for example, the third order viscous hydrodynamics, not the DNMR? How do you think?
Well, you don't
these trajectories will
have.
be different?
You don't have. If you're not using DNMR, if you're using something like just a gradient expansion of equilibrium currents, then you don't have a lot of these trajectories because most of these trajectories are produced from varying your initial conditions.
I think you will have the same freedom, right? But going to the third order viscous hydrodynamics, because using DNMR, you are stopping at the second order. So I think
you mean gradient expansion, or do you mean?
Yes.
So from what I know, DNMR is different than a gradient expansion. It's not exact. It's the dynamics are different, right? Like pi mu nu and the bulk pressure being their own independent viscous currents is different than doing a gradient expansion and going and having pi mu nu equal to sigma mu nu to eta plus some higher order terms or something like that, right? Because if pi mu nu is sigma mu nu, then it's completely determined from your flow, right? But the point is that pi mu nu and pi in DNMR is not completely determined from your flow.
Right, but it is truncated in the inverse Reynolds number and the
it is truncated,
number, right? So I think that's what he says.
I think I misunderstand the question, but
So I think George commented on that we need to rederive the conditions again for third order viscous hydrodynamics as well. So I saw, Mike, you raised your hand. Do you still have a question?
Yeah, just a comment related to what Ors and others were discussing. So yeah, I mean, also for other fundamental things like the pressure anisotropy, you can see conditions where you can get a negative pressure, right, in viscous hydro. But if you allow it to continue to run, it will go back positive and go back on. And if you were to start throwing out those trajectories where it's making a mistake, but it's not too far from the truth, it somehow suggests that we're killing too much phase space, but that's just my feeling.
That was my worry, yeah.
Okay, so I think we thank our speaker again. So thanks, Travis. And then for the last talk in this session,